We're going to take a look at a visual representation of a Taylor polynomial. Now, up here in the top left, you see the function that we have on the screen right now is the sine of x. Right now, we have a 0th degree Taylor polynomial, and that's actually the x-axis right now. That would just be y equals 0. And right now, our center is at 0. And as you see, there's 3 sliders up here at the top. The first one is going to be our center. The second one is the degree of polynomial that we're going to use, and then we're going to evaluate these at different places to see what kind of error that we end up with. So let's say that we have our center at 0, and notice as we start increasing the degree of our polynomial, now this is a first degree Taylor polynomial, and down here in the left-hand side, you can see that the Taylor polynomial would actually just be x here, and since we're evaluating at the center, there would be no error. Now, as we increase this, as we go from n equals 0, 1, 2, 3, you see as we start increasing our accuracy as we move away from our center. Now, if you're paying attention, notice that n equals 2 didn't change because sine's an odd function, which means it only has odd powers, so that wouldn't change. So notice that n equals 3. Now our blue polynomial matches the sine curve farther away from the center. And as we increase our degree, our polynomial, we get farther and farther away from the center. We get more and more accuracy. Now, notice in this case, down here in the bottom left, we have a 5th degree polynomial, and it matches, looks like it's pretty good out to about positive and negative 3. See, if we were to go, let's go over here to the right. If we go to about where 3 is, I'm trying to get the stop, you see we only have an error of 0.38 between our approximation, which is the blue curve, and the actual curve sine x, which of course is the black curve there. Now, like always, it generally happens with our approximations. The farther we get away from the center, notice our error is getting much, much worse. So let's go back to our center and notice that we can actually, it's not stopping there. If we really let the Taylor polynomial go up in power, notice we're matching the curve farther and farther away from the center, and you see that we can evaluate it farther and farther away from the center and still have basically no error in our calculation. All right, let's go back to our center here. Now, everything would stay roughly the same. I'm just going to back that down a little bit. If we move our center. Now, of course, our Taylor polynomial changes because for every term, instead of just an x, we have our x minus our center. So if we go over here to say, if we center at 1 now, you see every term of our Taylor polynomial, instead of an x, we have an x minus 1. But all that does is just shift the entire approximation curve. It doesn't change how far it approximates away from the center or anything like that. So Taylor polynomials are very useful for approximating curves. However, if you're using a finite degree Taylor polynomial, as you see, it can't model the curve everywhere. It can only go a certain distance away from the center, and then you're going to start developing errors. A little bit later on, we see that we take these Taylor polynomials and let the degree go to infinity, which means for a lot of curves, we can model them for everywhere, from negative infinity to positive infinity.